Hey y'all, in the last video we talked about Kepler's second law, which states that an object in orbit sweeps through equal areas in equal times. Today's video is going to take us from Kepler's second law to his third law.
I feel like an astronaut in what you know about rolling down in the deep.
Alright, so it's the last video in our Kepler series for now. Alas, well, the good news is if you like math, we're going to go over how to get from Kepler's second law, which we proved in the last video, to Kepler's third law, which states that the period of an orbit squared is proportional to the semi-major axis of the orbit cubed. The other good news is that if you don't like math, we'll soon be done with the derivation of Kepler's laws, and hopefully you'll have a more concrete understanding of these physical laws. Equal areas in equal times means that the change in area an object sweeps through over the time elapsed must be equal to a constant. That constant is L over 2m, as we showed in the last video. Once the object has completed a period, it will have swept through the entire area of the ellipse, so we can rewrite the above equation as the area, A, equals L over 2m times the period P. Now the total area of an ellipse is pi times the semi-major and semi-minor axis, A and B, so we can substitute this expression in for A. We can divide both sides by p and square them for some convenient substitutions later on. Let's start by making a substitution on the left-hand side of the equation. The relation between the semi-minor and semi-major axes of an ellipse is as follows. B squared equals A squared times 1 minus the eccentricity E squared. If we plug this into our equation above, we get pi squared times A to the fourth times 1 minus E squared over P squared. Now, let's move to the right-hand side of the equation. We showed in our proof of Kepler's first law that the distance r between the object in orbit and the focus is equal to the semi-latus rectum over 1 plus E cosine theta, where the semi-latus rectum is equal to L squared over GMM squared. At aphelion, the farthest point on an ellipse from the focus, theta equals 0 and r equals A times 1 minus E. We can apply these values to our equation above. From observation now, we can see that this equation shares some of the same parameters as our equation that contains L squared over 4m squared. If we manipulate it a bit, we get L squared over m squared equals A times 1 minus E squared times GM, which we can now plug into our initial equation. We now see that pi squared times A to the fourth times 1 minus E squared over P squared equals A times 1 minus E squared times GM over 4. We can cancel out like terms to get P squared equal to 4 pi squared times A cubed over GM. Since our other values in this formula are constants, P squared is proportional to A cubed. And voila! We just proved Kepler's third law.
Slow motion, yeah. I feel like an astronaut in the ocean, like what you know about rolling down.